If size is increasing area-wise, so that is superficial expansion. And the last part is when the size is increasing volumetrically, right? So the third part is cubical expansion. So when the size of the object increases volumetrically by increasing the temperature, Ikra, who is Ikra? Yeah, so when the size of the object increases volumetrically by increasing the temperature, then it is called cubical expansion, right? So the change in volume. So if we have this volume of the object, right? So then the length of this object and all the other parameters will change, right? So every other parameter will change. So its length will become this, and its area would become this, and everything will increase, right? In this manner. So this is whatever the volume is, initial volume, and then the final volume is V prime, right? So increase in volume would be how much? Let's say this is V prime. So increase in volume is V prime minus V, old volume minus new volume, and that is delta V. And this would be equal to gamma, whatever the coefficient is, and then the volume original, and then change in temperature, as we have studied in the previous case. So again, this gamma is coefficient of cubical expansion, right? So this is the coefficient of cubical expansion. And we have seen that how these, so then we'll study about how these coefficient of expansion are related with each other. So how this alpha, this beta, and this gamma, all these expansion are related with each other, right? But before we do that, let us do one question, and then that would be very clear to understand, right? So let's say that, yeah, oh, we don't have any book in here. Yeah, so let me bring the book in here, and then we will do one question from the book, and that is very helpful. So we understood that whenever we are increasing the temperature, the size of the object is changing. If it is changing linearly, so we will have linear expansion. If it is changing area-wise, so we'll have a superficial expansion. If it is changing volumetrically, so that would be cubical expansion, right? So on the basis of those, let us try to do some questions. Okay, so this is the question, right? So before we do this question, let us do a very simple question. So let's say that the length of a rod is the length of the rod, and let us write it as a steel rod is let's say 45 centimeter, right? By changing the temperature from 5 degrees C to not 5 degrees, let's say from 25 degrees C to let's say 40 degrees C. Its length has become let's say 50 centimeters, right? Then we have to find out then find out the coefficient of linear expansion. So what are the things which are given? We are given the original length L, right? This is 45 centimeter, which is 0.45 meters, right? And then we have temperature, which is initial temperature. This is, let's say, 25 degrees, right? And then we have final temperature, which is what? So final temperature is 40 degrees. And then the new length, this length has become 50 centimeter, which is zero point 0.5 meters, right? So then all the things are given, and what do we know? We know that the change in length that would be equal to alpha length and delta t, right? So this would be the relation of linear expansion, right, guys? Yes, yes, this would be the relation, right, guys? So we know that what would be the delta L? Delta L would be how much? That would be zero point 0.5 minus 0.45. This is how much? This is 0.05, right? And then
Yes,
what do we have? And then what do we have? Then we can also calculate this delta T, right? So now we have delta L, we have delta T would be how much? Delta T would be change in temperature, T minus T naught. So this is 40 minus 25, which is 15 degrees, right? So we have delta T, we have delta L, and then we have this L also. So then we can calculate this alpha. So this alpha would be how much? That would be delta L by L into delta T. So delta L is how much? 0.05. And then this L is how much? That is 0.45. And then this change in temperature, that is 15 degrees, right? So this is how much? This is 9. And this is 1 by 9 into 15 degrees C inverse. So that is the answer, right? That would be the answer. And if we calculate this thing, so this is how much? 1 by 9 into 15 is how much? So 135, and yeah, I don't know how much it's. So whatever this value is, so this is how much? 1 divided by 135. This is 0.007 degrees Celsius equals. That is, yeah. Is this thing clear, guys? Is this thing clear?
Yes, sir.
Yeah, so what part did you guys note down in the earlier class? Did you guys note down this part? Thermal expansion, linear expansion. Did you guys?
Yes, sir.
Yeah, so then please note down from here, right? Please note down from here. And today I want to complete until late 18th, right? So that part I want to complete. So just quickly do all these. So then after this we'll do an NCRT problem, and then we'll talk about the yeah. Whenever you guys want to just go down to the so you have to only use this relation, right? And in this part, I didn't give the coefficient of linear expansion, but I gave all the other things that you can calculate. So in these type of question, you will be provided either this alpha or this temperatures or these length. So you will be given all these values, right? Maybe they can ask you the change in length, and maybe they can ask you this final temperature. So all those things they can ask. So we'll see the next question, that how can we get that whenever you guys have noted it down, please Okay, Ilham is there. Yeah. Whenever you guys want me to scroll down, then
Done, sir.
then-
Hello, sir. Sorry,
yes,
sir, I'm late.
yeah, no worries, no worries. So we just yeah, we just started and we just did this cubicle expansion. So you just take the screenshot of this part.
Okay, sir. Okay, sir.
Yeah, just take the screenshot. And then we have done one question about this thermal expansion. So we are still doing this thermal expansion. Yeah, so while Amna and Ishita, they are noting it down. So let me, yeah, did you take the screenshot, Alarm?
Yes, sir.
Yeah. So what did we do? We understood about this cubical expansion. So in the earlier class, we talked about a linear expansion. So we are increasing the temperature of an object and it is increasing linear, right? So then that is called the linear expansion. If it is increasing area-wise, that is superficial expansion. If it is the volume of the object is increasing, so then that is called the cubical expansion, right? And then we did this problem about this linear expansion, right? So there will be one more problem related to this linear expansion, and whenever you guys have completed now, and this chapter is a pretty easy chapter, right? There are only few concepts, and if those concepts are clear, then this chapter will be done. So one is this expansion, and the other ones are the heat. So we are talking about the heat in this chapter, right? In subsequent topics, we'll see that how we can calculate. Yeah, but before we do that, please tell me whenever you guys. So in some type of question, they will say that, let's say that the length of the rod is something, and by applying some heat, the temperature, the length has increased by 20%. So then we can calculate the change in length, and they will give you some coefficient, and then you can find all these things. Yeah, but the idea would be same, right? Okay, done, everyone. Done, guys. Noted.
Yes, sir.
Okay. Yeah, let us do this question. But yeah, before we do that, let us talk about. We know that what are alpha, beta, and gamma. Now we know that, right? So the other topic is relation between coefficients of expansion, right? So we have alpha. This is a coefficient of linear expansion. And then we have beta, this is coefficient of superficial expansion. And then we have gamma, which is coefficient of cubical expansion. Right, so we saw that area is what? Area is length square, right? The dimension of area is length square. And we will see from another example also, right? So we'll see from another example that how this is related, right? So what do we know? We know that delta L, this is equal to alpha L delta T. We know that delta A, this is equal to beta A delta T. We know that delta V, this is gamma V delta T. So these are the three relations that we know that area is length into square, right? So length square. So if we calculate from dimensional analysis, if I calculate the relative error of A, what would be that, guys? What would be that? Yes, what would be that? You guys have done the error.
Delta uh, L2 minus L1 whole square by L square.
So this is directly delta L by L2. This comes in here, right? The power comes in the,
Yes, sir.
so yeah, this you guys have learned in dimensional analysis, right? Right, everyone.
Yes, sir.
Okay, and then we have yeah. So then we know that delta A by A. From here we can see that delta A by A is beta delta T, and delta L by L. Delta L by L is alpha delta T, right? So delta T cancel, and we will get beta equals to 2 alpha. Or we can write alpha is beta by 2. So this is the relation between the coefficient of superficial expansion and linear expansion. This we have got. Or we can also see from here also that area can be length into breadth also, right? So if I also calculate delta A by A, so that would be again how much, guys? What is the product? This is delta L by L plus delta B by B. Correct, guys?
Yes, sir.
So we know that this is again linear expansion, so this would be alpha delta T. This is again linear expansion, so this would be again alpha delta T. So again we will get this 2 alpha delta T from here also, if the area is length into breadth. So from here we'll also get this thing, from here we'll also get this. So ultimately we'll get the same result, right? So ultimately we will get beta as 2L. This is one relation. The other relation is volumetric expansion, right? So we know that volume is length Q, right? So then what would be this thing? Delta V by V would be how much, guys? How much would be this?
3L by L.
V delta L, right? So then we know that again this is gamma and this is 3 gamma delta T, and this is 3 alpha delta T. So this will cancel, and we will get gamma as 3 alpha, right? Or we can write or we can write alpha as gamma by. So these are the relationship between the coefficients of expansion. So beta is 2 alpha and gamma is 3 alpha. So these are the relations. And in the NCRT textbook, they have also shown this superficial expansion by giving an example of a rectangle, right? So let's say we have a rectangle, and then what do we do? So this is, let's say, A, and this is B, right? And we are increasing the temperature of this thing. So if we increase the temperature, so this will be increased from here, right? This part will increase delta A. Correct? Is that correct, guys?
Yes.
Yes, sir.
And this part will increase by delta B, right? So the new area would be this. So this is the new area, right? So then if we calculate the new area, so that would be how much? A prime is this length, right? This length is how much, guys? This length is
One by n.
A plus delta A. This is the length, right? Original area was how much? Original area was A into B, right? This is the original area. Now the new area has become A prime. This is the new area, right? So new area has this length, which is length into breadth, right? So this is A plus delta A, and breadth is how much? What is the breadth, guys? What is the breadth? This is the breadth, right? From here to here.
B plus delta P.
B plus
B.
delta B, right? So this is the new breadth. So this would be the area, guys. Now this would be the area. So this would be the what? So this would be the new area, right? This is the new area. Okay, and this is what we are finding now. Whose length is this thing? Whose breadth is this thing? So if we calculate, this would be AB plus A delta B plus B delta A plus what? Delta A into delta B. Right? These are small quantities. If we multiply 0.001 into 0.007, so this would be 0.000000. Very small thing, right? So this we can neglect. Is this thing clear, guys? Is this thing clear, guys?
Yes, sir.
Okay, so this is our A prime. And the change in area, right? The change in area, oh, we will calculate that later, but let us calculate this. So change in delta B, this is linear. Delta B is linear expansion. So that would be how much? That would be alpha and B and delta T. Similarly, change in A, that would be how much? Alpha and A and delta T. Is this part clear? Because delta B is linear expansion, right?
Yes, sir.
This is alpha B and delta T. Delta A is alpha A and delta T. So these are the two things. And then this would be how much? So this is AB, right? Plus this is AB alpha delta T plus AB alpha delta T. So now what we need to calculate? Change in area. Change in area, which is delta A, which is what? Which is the new area minus the old area. So this was the old area, right? This was the old area, and now it has become a bigger area. So change in area would be how much? A prime is AB plus AB delta alpha delta T plus AB alpha delta T and minus A is A. So this part cancel out, and we have what? We have AB, and these are same. So this is 2 AB alpha delta T. Is this part clear, guys? Clear?
Yes, sir.
Yes, sir.
Okay, now you guys tell me from superficial expansion, you guys already know that what would be delta A. What would be delta A from superficial expansion? That would be beta and whatever the area was and change in temperature. Correct, guys? Right.
Yes,
Yes,
sir.
sir.
So, and we know that area is how much? That is A. So, beta A is AB delta T. So, delta T cancel, AB cancel, and we have beta, which is 2 alpha. So, this is one of the example of the perspective, right? This is how we have, but from the dimensional analysis, we can also, right? So, these are the things I wanted to tell. And then we'll do one question from the NCERT again. But before we do that, you guys, please, and if you guys have any doubts, please tell me. Where is RK? RK is not here. This was very important. Okay, so whenever you guys have noted, let and is my voice faint or okay, or you can hear me properly? Yes. Okay, yeah. You guys note it down and tell me whenever you want this.
Done, sir.
Done, guys. Okay. Yeah, then please. Yeah, whenever you guys have put it,
Done, sir.
done. Everyone noted.
Yes, sir.
Yes, sir.
Now let us do this question from the book. Yeah, this part we have done. Right? This thing we have done in this book. They have done differently, but yeah, we have done. What you guys have. Okay, so now let us do this question, and then this would be very clear, right? So, so a blacksmith fixes iron ring on the rim of a wooden wheel. So we have this wheel, right? So we have this wheel, and on this wheel, right, the iron ring, the diameter of the rim and the iron ring are right. So this is the wheel, and this is the iron ring, right? And this diameter is 5.231 meters, and this diameter, right? This one is how much? 5.243, right, meters. So if we want to fit this iron, right, in this ring, then we have to heat up this iron, right? Then we have to heat up this iron. So we have to heat up this iron ring so that it expands and its diameter becomes this, right? So what is the final diameter that we want? What is the L prime? L prime is 5.243 meters. Original length is how much? That is 5.231 meters, right? And the initial temperature, right? at 27 degrees C. To what temperature should the ring be heated? So of course we have to heat this ring rod, right? And up to what temperature? So T initial is given. T naught is given, which is 27 degrees C. We have to find out this final temperature, right? And what do we require? Because we know this relation from this one and this one, we can calculate delta L. And delta L is alpha L delta T. So delta L we know, this we can calculate. L and this is T minus T naught. So we know this thing, right? We know this thing. We know this thing. And we have two unknowns, this one and this one, right? So can we solve this part? Can we solve this part? Because there are two unknowns. We have only one equation. Can we solve this part? Yes, guys. Without knowing alpha, can we solve this for t? Can we solve this? Without alpha, can you guys solve this thing? Because delta L we can calculate. Delta L is new length minus the original one. So this is 5.243 minus 5.31. Yeah. Yes. No. Yes, Amna. We cannot calculate. So we require, this is 2, this is 1, and this is 0.1. Right. So we require this alpha, but they have not provided the alpha, right? So why they have not provided? Because in the NCRT book, they have already given all those tables. So they have given in the table form, right? The iron, the coefficient of linear expansion of iron, that is already given in this book. So that is why they have not provided this alpha in here. So alpha iron, right? Alpha iron, this we have to look from table. So let us look at the table. So this is how much? Alpha of iron we have to look, right? So this is the material iron. So the coefficient of linear expansion of iron is 1.2, and the order is also given here. This is not only 1.2. This is 1.2 into 10 to the power minus 5 per Kelvin. So it is given in per Kelvin, right? Yes, I think 1.2 into 10 to the power minus 5. Okay, so this is given 1.2 into 10 to the power minus 5 Kelvin per Kelvin, right? So now let us, now we can put all the values and then we can calculate, right? So how much would be this thing? So the delta L is 0.012. L is how much? L is 5.231. T we don't know. T naught is, oh, alpha also. So alpha is 1.2 into 10 to the power minus 5 per Kelvin, right? And this is T, we don't know, T naught is 27, right? So this would be how much? This is 0.012 divided by 5.231 into 1.2, and this is 10 to the power 5, right? If we cancel this thing out, if we cancel this thing out, so this is 12, this 12 cancel. and this is equal to t minus 27. This is how much? Uh, 10 to the power 6. So 1, 3, and 3. Right? Divided by 5, 2, 3, 1. So how much is this? Right? How much is this? 10 to the power divided by 5 to 1. So 191.16. 191.16 equals to t minus 27. So t is 191.16 plus 27. This is how much? 168.9211.218 degrees Celsius. What is the answer to grade 1? Right? Is this thing clear, guys? Is this question clear? Yes, guys. Is this
Yes,
question?
sir.
Okay, please note it down and then we'll do another topic. Please note it down. Yeah, whenever you guys want to scroll down, please do that. Done, guys. Yeah,
Yes, sir, done.
completed. Did you guys look down on these noted? Done, everyone.
Just 1 minute, sir.
Okay.
Done, sir.
Yeah. What about you, Rishita and Amna? What about you guys? Done. Done, guys. Guys, what about you guys? Rishita and Amna, what about you guys? I guess now let us talk about what happened? Not right. Okay, so why this happens, I don't. Yeah. So what I was saying that we have understood. Is my voice audible, guys?
Yes, sir.
Yes, sir.
Yeah. So what I was saying that we have seen up until now that how length, how area, how volume changes. Now what about the density? So density variation with temperature, right? So how the density of the matter will change. So we know that what is the density? How do we write the density? Do you guys remember? What is density? Yes, come on, guys. So we have done this in liquid and fluids. Mechanical properties of fluids. The second thing that we did was this density. What is density, guys? Mass by volume, right? So this is mass by volume, right? So this is how the density is related with mass and volume, right? So we know that mass of the object will remain same because of the conservation of energy, right? So mass of the object cannot change. So only the volume will change, right? So if we write delta rho, right? If we write delta rho, so that would be how much? That would be m by delta v, right? So if we write the value of delta v, so this is how much? Yeah, I should write in different manner. So let me write it in that. Right. Okay. So this is my original. Let's say this is my original mass and volume. And if I apply some temperature, so by applying some heat, my density has become rho prime, which is mass by volume prime. Right. This is the thing that I need to figure out, right? So rho prime would be how much? I can write V prime. I can write V prime as how much? V prime is V plus delta V. This is the change in volume. And if I put this value in here, right? So rho prime, this would be M by V plus delta V, right? So I know that I can take this V common out C and 1 plus delta V by V, right? So this is this. And I can write this thing as how much I can write. So this M by V is my original volume. And this is 1 plus delta V by V, right? So then this would be how much? I know that my volume changes as so delta V is how much? This is gamma delta uh, gamma V and delta V. That is how the volume changes. So if I put that value in here, so this is 1 plus gamma v delta t, right? So then this would be how much? So rho prime, and if I take the binomial expansion of this thing, right? So if I can take this in the upper side, so this would be how much? This rho would be 1 minus of gamma v delta t. Oh, so this would be, if I'm calculating delta v by v, so this v would not be there, right? Because delta v by v, that is gamma delta t. Right, so this is gamma 1 minus delta t. Did you guys understand that why this would be 1 minus gamma delta t? Did you guys understand this part?
Yes, sir.
Yeah, because this is 1 by 1 plus gamma delta t. So I can write this as 1 plus gamma delta t inverse, right? And if these things are very small, so from binomial expansion, I can write this as delta t. So can you guys tell me, my volume is, my density is decreasing or increasing? What is happening to my density? Is it increasing or is it decreasing? Yes, guys. My density is increasing or decreasing?
Increasing.
Increasing. Okay, so if I write this in this way, so you understood that my original is this. Original density is this thing. My new density is rho prime, right? Is this clear?
Yes, sir.
So, so if I write my rho prime as, if I break this thing, so rho minus rho gamma delta t, right? So if I ask you guys that which one is greater, rho prime or rho? Because you are subtracting this thing from rho, right? So you are subtracting, you are taking out this portion from rho, which means that this rho prime is coming out to be smaller or larger. Yes, rho prime, if you have, let's say 3, this is 5 minus 1. So you are taking, this is 5 minus 2, right? So you are taking 2 from 5 and then it is becoming 3. So which one is larger, which one is smaller, which one is greater, which one is smaller? Yes, yes, guys. Who got disconnected? So Amna got disconnected. So which value is larger, 5 or 3? Obviously, 5 is larger, which means that this row is larger, this row prime is smaller, right? So this row is bigger, this is smaller. So now you tell me, my density is increasing or decreasing? Yes, density is increasing or decreasing? Yes, right. Density is increasing or decreasing? New density is smaller, the original was larger, bigger. So this has become smaller. So how can it be smaller if it is decreasing or increasing? Increasing. Okay, so I had, right, let's say, Let's say I have a container and four particles are there in this container. So my density is how much? Whatever the mass of this four particles, right? Divided by the volume of this container. Let's say this is a cube. So let's say this is a cube, right? This would be the density. If I increase the volume, I have increased the volume, and now the masses are same. So now the density will increase or decrease. Now you guys tell. Because I have increased this volume A prime, so my density will increase or decrease? Yes, density will decrease, right? Because this is bigger now. So if I increase the volume, my density will decrease. So rho prime is smaller, rho is larger, so density will decrease, right? Decrease. So now did you guys understand that why this would decrease? If you increase the volume, right? By if we are increasing the temperature, that will increase the volume. If volume is increased, we can see that this is inversely proportional. So if volume is increased, then rho will decrease. So let's say that rho is 3 by 4, but the new rho is 3 by 5. You have increased this thing. So then this would become smaller, right? So if we increase the volume, rho will decrease. So that was what I was telling. And this would be decreased by this much amount. So this would be the decrease in the density. Right. Okay, so you guys please note down this part, and then we'll talk about one property of water which is very crucial. So we have understood that how length, area, volume, and density will change by increasing the temperature. Quickly, you guys note it down, and if you guys have some doubts, please tell. Yeah. And whenever you guys have any confusion, please let right. Yeah, whenever you guys have completed, please tell me. I wanted to complete up to latent heat. So, what?
Done, sir.
Done. Okay, so all of you noted, all of you guys noted? Yes, everyone noted.
Yes, sir.
Okay. So now there is a peculiar property of water, right? We know that now what do we do? We know that if we increase the temperature, the volume should increase. If we increase the temperature, the density should decrease, right? This is what we know. But this anomalous anomalous property of anomalous behavior of water. right? And this is very so the nature is we don't know how this nature works, but somehow if we increase the temperature of the water, then at certain point its volume decrease and its density increases, right? So the variation of volume, right? Volume variation. So the usual thing is that the volume should increase, but in the anomalous property of this is 100 degrees C, and we are starting from zero. So starting from zero at a certain point, it decreases and then it increases, right? It decreases first and then increases, right? So this is called the anomalous behavior, and this temperature is 4 degrees C, right? So at 4 degrees C, the volume of the water is minimum, right? This is volume, and this is temperature. And similar thing happens with the density always. So density variation. Density variation, and we know that the usual thing is that the density should decrease. But for the case of water, it increases and then it decreases, right? So this is again 4 degrees C, and this is 100. This is density, right? And this is temperature. So this is in kg per meter per ml, right? So this is how the density varies. So where is the density maximum? Where is the density maximum, guys? Density of water is maximum at what temperature? Yes, guys. Density of water maximum at what temperature?
100.
Density of water maximum from this graph. From this graph, this is the maximum point. So at
Yes.
4 degrees, and density decreases, right? So this should be downward, right? So I should write from here. Yeah, but so at 4 degrees C, the density is max, right? And this happens. So due to this, the marine life is possible. So whatever you see, those aquatic creatures in the ponds or in the seas, those happens only because of this thing, right? Because let's say in cold areas, the water should freeze, right? So if all the water is frozen, then how is the life of those aquatic animals are possible, right? But due to this density variation, so the top of the layer is frozen. But below that level, the density of the water is maximum, and it is at the 4 degrees Celsius, right? So then the water is not freezed at that point. So then the aquatic life is possible. So due to this behavior, marine life is possible. This phenomena is very crucial for the aquatic animal, right? Did you guys understand this anomalous behavior?
Yes, sir.
Yes, sir.
Yeah, then please note it down. Right, so usually in the earlier cases, what did we see? We see that if we increase the temperature, volume will increase. But we see that if we are increasing the temperature from 0 to 4 degrees C, the volume is decreasing. And now it is showing the actual behavior. Similarly, we saw that the density should decrease. But from 0 degrees C to 4 degrees C, the density increases. So it shows quite the opposite nature that we have done. And this nature is very crucial for the aquatic life. Yeah, whenever you guys have completed noting it down, please tell. I have just explained this thing, but yeah, you guys can write on, right? Because now you guys understand, so you guys can write. Okay, whenever you guys have completed noting it down, please tell. Yes, whenever you guys have noted it down, please tell.
Sir, can you scroll?
Yeah, so this part here, I'm not reading that. Yes, noted everyone.
Yes, sir.
Yes, sir.
Good. So now let us understand about. Yes. Now let us understand specific heat and latent. What is the word? What is the meaning of the word latent? Guys, yes. What is the meaning of the word latent? So the meaning of this word latent is hidden, right? Meaning of latent is hidden. So we'll talk about this latent heat later, but let us first talk about this specific heat, right? So what is the specific heat? if you have, let's say, if you have some container, right, and you have, let's say you have 2 kgs of, let's say you have, yeah, let's say you have 1 kg of water, and you want to increase the amount of this water, right? You want to increase the temperature of this water from, let's say, 5 degrees C to, let's say, 15 degrees, right? So then you will require some heat, right, guys? And let's say if you have same beaker, but the amount of water is, let's say, 5 kg. And again, you want to increase the temperature from 5 degrees C to 15 degrees C, right? So if again you want to increase the temperature, then you require some heat, right? So in which case you will require more heat, guys? Which case? Heat up 1 kg of water would be uh, quick, or to heat up 5 kg of water, which one would be quicker? Yes,
1 kg.
1 kg would be quicker. So the amount of heat that you require, that is uh, that is seemingly dependent upon this mass of the liquid that you want to heat, right? And
Yes, sir.
also, we see that this is also dependent upon this temperature also, right? This is also dependent upon this temperature. So, so we can write that this amount of heat would be equal to, if we remove this proportionality, this is also dependent upon change in temperature. How much we want to increase the temperature, right? So this, if I remove the proportionality, so that would be MC and delta T, right? So this is called the specific heat. So specific heat is what? Yeah, where should I write? Yeah, let's write it. So the amount of heat required to increase the temperature of a unit mass object to 1 degree Celsius, or to unit degree, right? Unit degree. And that would be degree Celsius, degree Kelvin, degree whatever. So if we are taking SI unit, so that would be degree Kelvin. If I'm taking CGS unit, so that would be degree Celsius, right? So in CGS unit, heat is represented as, right? Heat is represented as calorie, right? And in SI unit, so in CGS, your temperature is what? Temperature is degree Celsius, right? In SI unit, heat is what? Heat is joules, right? And your temperature is what? Temperature is Kelvin. So these are the things that we have to remember, and this is very important thing, that 1 calorie. this is 4.2 joules. So remember this conversion. This is very important. Okay. So this is called the specific, and we have this molar specific heat also, right? So molar. Oh, the time is already over. Yeah. So we will talk about these things in detail classes, right? So these are very crucial, right? And you guys please note down this part, and then in the next class, so it will take two class more to complete this chapter, right? You guys please note it down, because only the remaining things are specific heat, latent heat, and conduction of heat, or transfer of heat. You guys quickly note it down, and then we will stop here, and in the next class we will continue from here. Whenever you guys have noted it down, please tell.
Done, sir.
Done, everyone. Okay, so yeah, see you guys in the next class, and yeah, you guys start revising whenever you're